Hello, in this lecture video, I am going to explain problems of semiconductor physics which comes under module 5 of engineering physics prescribed by VTU. The first problem is calculate the concentration at which the acceptor atoms must be added to a germanium sample to get a p-type semiconductor with conductivity 0.15 per ohm meter given the mobility of holes is equal to 0.17 meter square per volt second. So here the given data is electrical conductivity sigma that is equal to 0.15 per ohm meter and mobility mu is equal to 0.17 meter square per volt second and charge on the electron that is 1.6 into 10 to the power minus 19 coulomb. So here we have to calculate the electron concentration n. So the electron concentration n is given by sigma by mu e. So substitute the value of sigma and then mu and e in this equation. We are going to get that is 0.15 divided by 0.17 into 1.6 into 10 to the power minus 19. After simplification, the value of n is equal to 5.515 into 10 to the power 18 electrons. So this is what the answer that we are getting after calculation. For intrinsic germanium arsenide, the room temperature electrical conductivity is 10 to the power minus 6 per ohm meter. The electron and hole mobilities are respectively 0.85 meter square per volt second and 0.04 meter square per volt second. Calculate the intrinsic carrier concentration at room temperature. So here the given data is sigma I is equal to 10 to the power minus 6 per ohm meter and mu e is 0.85 meter square per volt second and mobility of hole is equal to 0.04 meter square per volt second. So we have to calculate what is Ni. So using the formula, we know that sigma I is equal to Ni into E into mu E plus mu H. So this is the formula. So Ni is equal to sigma I by E into mu E plus mu H, that is equal to 10 to the power minus 6 divided by 1.6 into 10 to the power minus 19 into 0.85 plus 0.04. So on simplification, we are going to get the value of Ni is equal to 7.023 into 10 to the power 12 per meter cube. This is what the value of Ni we calculated. The next problem is the electron concentration in a semiconductor is 5 into 10 to the power 17 per meter cube. Calculate the conductivity of the material if the drift velocity of electron is 350 meter per second in an electric field of 1000 volt per meter. So here given data is n is equal to 5 into 10 to the power 17 per meter cube and drift velocity Vd is equal to 350 meter per second and the value of E is equal to 1000 volt per meter. So here we have to calculate what is electrical conductivity sigma. So as according to quantum free electron theory, we have sigma is equal to Ne square tau by m and Vd is equal to E into E tau by m. So sigma is equal to, finally we after simplification we are going to get sigma is equal to Ne Vd by E. So that is equal to 5 into 10 to the power 17 into 1.6 into 10 to the power minus 19 into 350 volt divided by 1000. On simplification, the value of sigma will be 0.028 per ohm meter. So this is what the value we are calculated here and this is the way of calculating the parameter asked in this problem. Now the another problem is the Hall coefficient of a specimen of a doped silicon is found to be 3.66 into 10 to the power minus 4 meter cube per coulomb. The resistivity of the given specimen is 9.93 into 10 to the power minus 3 ohm meter. Find the mobility and density of charge carrier assuming single carrier conduction. So here the value of RH is equal to 3.66 into 10 to the power minus 4 meter cube per coulomb and the resistivity rho is equal to 9.93 into 10 to the power minus 3 ohm meter and the charge on the electron is equal to 1.6 into 10 to the power of minus 19 coulomb, and what is the value of mu and n. That is what the parameters asked in this problem. So we know that the value of RH, that is Hall coefficient RH, is equal to 1.18 by NE. So that is equal to 1.18 by E into RH, that is N is equal to 1.18 by E into RH. So substitute the value of E and RH here. So after simplification, we are going to get the value of N is equal to 2.015 into 10 to the power of 22. Okay, that is what the number of electrons per meter cube or charges per meter cube. And further, the value of mu is equal to RH by rho. So the value of RH is given, that is 3.66 into 10 to the power of minus 4 divided by rho is nothing but 9.93 into 10 to the power of minus 3. So on simplification, the mobility mu is equal to 0.0369 meter square per volt second. So this is what the way of calculating the value of n as well as mu. The another problem is an n-type semiconductor specimen has Hall coefficient is equal to 3.65 into 10 to the power of minus 4 meter cube per coulomb. The conductivity of specimen is equal to 112 per ohm meter. Calculate the charge carrier density and electron mobility at room temperature. So this is what the problem. So here the value of RH is 3.65 into 10 to the power of minus 4 meter cube per coulomb, and sigma is equal to 112 per ohm meter, and E is equal to 1.6 in 10 to the power of minus 19 coulomb, and we have to calculate what is mu and n. So we know that RH is equal to 1.18 divided by NE. So we get N is equal to 1.18 by E into RH. So on simplification, we are going to get the value of N is equal to 2.026 into 10 to the power of 22 charges per meter cube. So further, mu is equal to sigma RH. So by substituting the value of sigma and RH here, we are going to get the value of mu as 0.04088 meter square per volt second. So this is the way of calculating the parameters asked in this problem. Now the another problem is the effective mass for the electron in germanium is 0.55 m0, where m0 is the free electron mass. Find the electron concentration in germanium at 300 Kelvin, assuming that the Fermi level lies exactly in the middle of the energy gap, given that the energy gap of semiconductor is 0.66 electron volts. So this is the problem. The solution is, here the mass m0 is equal to 9.1 into 10 to the power of minus 31 kg, and m star, that is nothing but 0.55 into 9.1 10 to the power of minus 31 kg, and the value of T is given, that is 300 Kelvin, and energy gap is equal to 0.66 electron volts. So the Fermi level is exactly in between the value of energy gap, that is EF is equal to Eg by 2, that is equal to 0.66 by 2, that is equal to 0.33 electron volts. And we know that the number of electrons is equal to 4 root 2 into pi m star kt by h square all to the power of 3 by 2 into the power of EF minus Eg by kt. So this is the formula for electron concentration. So substitute all the parameters in this formula. Then after simplification, we are going to get the value of Ne, that is number of electrons per unit volume, is equal to 2.956 into 10 to the power of 19 per meter cube. So this is the data we are going to be calculated here.